Good morning. Thanks for coming to the second invited session. I'm Ellen Longmire from the University of Minnesota, and it's my pleasure to introduce our speaker today, who is Edouard Barrocal. He's a native of France, but he completed his PhD in Cranfield University in 2006 in England. And then he moved to Lund University in Sweden, where he was a postdoc at first, and he has stayed there ever since. He's currently an associate professor, and he's in the division of combustion physics. His expertise is in the area of optical methods, and I think he's going to talk with us about applying optical methods in sprays, using a very specific method that he's one of the inventors of. So, Thank you very much, Edouard.
Thank you. Thank you very much for this introduction. I would like to thank also the organizing committee to invite me to this conference and give me this great opportunity to present my research work. So before starting, I would like to answer this question. Why are sprays so important? Every time you are driving your car, you are using a spray system thousands of times per minute, either diesel sprays or a GDI sprays. When you are flying, for example, to come to this conference, your plane is burning tons of kerosene. And the way you burn the fuel is directly driven by how you inject it. So looking at this injection of liquid fuel is very important, and this is done through an atomizing sprays. And to look at those sprays, we use laser techniques. And one of the most used techniques to look at sprays for visualizations is laser sheet imaging. And this has been done already back in the 80s. In 1984, Melton and Verdick did one of the first planar imaging of a sprays with Exciplex lift, and they could separate the liquid phase from the gas phase. And in this very early paper, they mention that the scattering from the numerous small droplets will remain a serious problem for any optical techniques used in these down sprays. Later on, in 1988, Cavalier et al. Did the first planar imaging in a diesel spray. And once again, they reported in their paper the presence of interference and multiple scattering effects presents challenges for the application of 2D scattering techniques. Finally, in 1993, Ie Kosoda and Kamimoto in Japan did the first papers on liquid leaf and mist-scattering and taking the ratio, trying to extract the outer mean diameter, droplet size in 2D. In this very early paper, once again, they mention the fluorescence to scattering ratio method proposed here is liable to be influenced by the multiple scattering. So, in this talk, I will obviously talk about multiple scattering and how to first to understand this issue. Then I will propose a technique based on laser sheet imaging called SLIPI, Structured Laser Illumination Planar Imaging, to solve this problem. Then I will show some results based on averaged imaging for droplet sizing and also thermometry. I will show to you how it's possible to obtain instantaneous SLIPI images. And finally, how we can apply the technique to transient sprays. So let's start with multiple light scattering to describe this effect and how we can possibly suppress it. So if we take a spray and you just light it with a laser, you can actually recognize that some of the light is scattered outside of the illumination beam. So this is due to the fact that photons scattered multiple times and get into the camera. Now if you increase the pressure of injection, this effect is more and more visible. So if you increase from 20 bars to 60 and 200 bars, then the number density of droplets is much higher, and this effect is very visible with a lot of multiple light scattering around the illumination volume. So let's have a look to this beam crossing this cloud of droplets. At this distance, below the nozzle, you can assume you have now spherical droplets. Near the nozzle, it's the spray formation region, where you will have some ligaments and irregular liquid structures. But further down, you should obtain micrometric spherical droplets. And then, in this region, you can assume that your beam is exponentially reduced as a function of the Beer-Lambert law. So it's related to the distance you cross, the number density of droplets, and the extinction cross-section, which is the sum of the scattering and absorption cross-section. Now you can also extract the mean free path length, which is the average distance between two scattering events. This can be calculated by the inverse of the number density times the extinction cross-section. So if now you take the full distance of your spray and you divide by the mean distance where you have a different scattering events, then you can extract the average number of scattering events. And this is what is called the optical depth, which tells you, in average, along the path of the beam, you have this number of scattering events. So you can use this quantity to define different scattering regime. If this is less than 1, so you have more or less only one scattering event in average in your medium. So this is usually not a problem, and most techniques assume this single light scattering. Now, if it's very, very dense, you are in the multiple scattering regime, and this is when the optical depth is above 9. In this case, the number of scattering events is more or less equal. You have as much as 2 or 3 or 4 or 5. It tends to be equal, and the diffusion approximation can be applied. But in sprays, we are in between these two regimes, between the single scattering and the multiple. So it's like the intermediate scattering regime, where the number of scattering events is between 1 and 9. So there's still some good information remaining in it, but it's covered by multiple light scattering, most of it. So what about now if we put a camera in front of it? So of course what we detect is a transmitted light, but the light that scatters around gets back into the camera. So we have those two components. And we want to filter out this multiple light scattering. So one very simple way in this case is to use a lens and to put an aperture at the focal of the lens. This is Fourier filtering. And what you do is only the collimated beam, the parallel photons, will just go through the aperture, while the scattered and multiply scattered photons will arrive with some angle, will not cross through. So it's quite simple, but very efficient on the transmission configuration. So now if we put a target in front of it, and we have a scattering medium of 50 millimeters with scattering particles of 10 microns and an optical depth of 10, you get this image of the star target, and you barely see it. But by doing this Fourier filtering, you can clean up your image, and suddenly you can observe the object behind the scattering medium. Now there is another concept, is if you send a very short pulse of light in this scattering medium, the multiple light scattering will travel around and arrive later in time, while the ballistic light, the light that is not scattered, will arrive first. So what you can do is to do a very short gating. Just take the first portion of the light arriving into the detector, and then you will improve your image contrast. So how do you do that? Because now we are talking about you have to gate light, and this has to be in a very short time scale. Usually the pulse used is in 100 femtoseconds, and the best gate will be a gate of 100 femtoseconds. But this is not possible yet, and usually what people use is a Kerr medium, where you can have a gating around 1.8 picoseconds. So how such a gate is working? You send a pulse of light with a vertical polarization, and just before detection, you have two cross polarizers. So basically, no light will reach the camera. Now, if you activate this Kerr cell with another pulse, you will create a birefringence effect that will rotate the polarization of the incident beam, and it will be a leakage into the camera. And to excite this medium, you use another pulse. So you send a pulse in a Kerr cell, and then you have a leakage, and then it reaches the camera. And the response of the Kerr medium, which is CS2 most of the time, is in the range of 1.8 picoseconds. So then you can time gate light at such a scale and get first photons reaching your camera. So this technique is known as ballistic imaging technique. And by doing so, you also improve contrast. So if you take, for example, the same test target star, a medium equally big, 50 millimeter, 10 microns particle, and optical depth 10, you will get such an image. In this case, I just simulated it. So these are the results from simulation. And then with no time gating, we have this image, and when you time gate, you can also improve the contrast. But what about now if we look from the side? Because we are interested in planar imaging. The advantage of laser sheet imaging is to have a section of the spray. Line of sight configuration, like transmission imaging, like I showed before, doesn't give you this sectioning capability, so you will have information integrated along the sprays. And this is why laser sheet imaging is very important for looking at spray systems. So now we have moved the camera from the side, and in this case, of course, we have loss of light, same than before, but we have also a signal attenuation. The signal from your light sheet that goes to the camera is also exponentially attenuated. So it's a slightly different configuration than before. And then you have the multiple light scattering. So what about using this same type of filtering from the side? The problem is if you have a photon that is singly scattered and it arrives at a given time, TS, and with a given angle, what's the difference between these singly scattered photons with the multiply scattered photons? A multiply scattered photons might arrive actually at the same time than the singly scattered photons. And it might also arrive with the same angle. So if you do a filtering based on the direction of the photons, like Fourier filtering, or based on the time, from the side, it will not work. So it's more difficult to remove multiple light scattering from the side than in a transmission imaging. So how can we do? The solution we propose is called structured laser illumination planar imaging. So what is behind this technique? How does it work? Let's take an example. This is just a cuvette with a normal light sheet crossing or fluorescing in water. And now the whole idea is to modulate in space this light sheet. So basically from this, we get this. And this doesn't do it all. This is just the first step. So you need to modulate in space the light sheet. Then let's put some scattering particles in this medium. And then we will look at this area and try to analyze what's happening to this modulation pattern. So we send a modulation that goes from a 0 to maximum intensity. And then we have this image from the side, and we will look first at this distance, A. And what we can observe is that the amplitude of the modulation has reduced as compared to at the entrance. And if you look further, you can suspect that this will also reduce furthermore. And this is what we have in B. So you have a reduction of the amplitude of the modulation. At the same time, what is the non-modulated component, this is not sent in the system. This is light that has been scattered around. It's non-modulated. You send a purely modulated light sheet. So you should not have this component doesn't come from your illumination. And this is multiple light scattering. So just from this basic concept, you can understand that by modulating your light sheet, it's like a fingerprint into your illumination. Now you can take advantage of it later on. So we want to extract this amplitude of the modulation. So this is the idea. This is the information we want to extract. How do we extract it properly? So this is a conventional laser sheet, so it's all homogeneous. And along the Y section here, we got the intensity. We assume it's a constant here. Now we modulate it. Here we have a modulation around the DC component, the conventional, and a modulated component. And what we want to extract is IS, is this amplitude of the modulation I was describing before. So, and you want to do that pixel per pixel. You don't want to lose any resolution on your image. And how can you extract this amplitude of the modulation without any loss in image resolution? You need to shift the line structures, as you can see, 1/3 of the spatial period, and record 3 images. From those 3, you do the sum up of the absolute value of the differences between each pairwise using this equation, and then you will extract your IS component, the amplitude of the modulation. Now, if you look at the difference between IS, I put it down here, and IC, the conventional, this distance here, it actually corresponds to all the contribution of the multiple scattering below. So all the light that is not modulated is, as I said before, come from outside the illumination plane. So now we've got those equations. We can apply it in a real case. So this is a cuvette with scattering particles. We move the lines. We record 3 images where we have a shift of the line, 1/3 of the spatial period. If you just sum them up 3 and you make an average, you will get the conventional components, which is similar than if you send an homogeneous light sheet, so no improvement there. And now if you apply the SLIPI equations, then you obtain this image. And you can see all the information from the sides of the cuvette is gone, the light scattering above and below is gone, and you can see the extension of the light as it propagates. And you can actually see also the profile of the light sheet, which is not homogeneous in this case. One of very big questions I always get is, why do you do it with 3 and not 2? It will be much easier. If you just take 2 modulated images and then you shift half of a period, what you will get this image. So you do remove everything around. The problem is you have those residual lines, because now you have 2 sinusoidal crossing, and if you just subtract them, at the crossing point, you will have a 0 values. So you got those lines, and that's the reason why you need 3 to do the operation. But I will come back to this later on in my talk. So let's apply the 3-phase and try to check out what's happening when we look at the light crossing this scattering medium. In this case, we have 15 microns particles in an optical depth of 4. So what you can see here, at the beginning, we are 2 millimeters near the edge of the cell. So it's not so much multiple light scattering between the light sheet and outside. But still, we can observe some differences, with SLIPI showing a nice extension of light, while here we still have some contribution of light outside of the illumination plane. Now, if we move the cell or we move the light sheet more inside, what we do is we increase the contribution of multiple light scattering. And at some point, we actually observe an increase of light intensity on the conventional. So this is, of course, the effect of multiple light scattering. You have more and more, and you don't see any reduction. The exponential reduction that is predicted by the Berlin law is not observed. But with SLIPI, you do observe it. And no matter how deep you go, you always have the same decay. Only the intensity is reduced due to the signal attenuation accordingly. So this is a very good proof that you extract single light scattering. And based on that, now you can use a technique to try to size or to find out the temperature or any quantities, because you know that what you get is really coming from the illumination plane and not outside. So let's use the technique for droplet sizing and spray thermometry. We have applied the technique in holocone sprays. This was the first ever SLIPI image recorded. And we can see the difference between the conventional, with most of the light in the central part, which should be hollow because it's a holocone spray. Of course, you have tiny droplets still coming back inside, but the signal should be much lower. And we can see how much we clean up the images. Then we decided to do the Leave Me droplet sizing approach. So the idea is you shine a droplet with a laser beam, you have a miscatched light. If the droplets are not too small, this is related to the surface area of the droplets. Now, if you put a dye on the droplets and you excite it, then you will have fluorescence. And by using a dichroic mirror, you can get a signal which is related to the volume of the droplets. This is true if the droplets are not too big, or if there is no, or if the concentration of dye is not too high. So all of this is true if the droplets are spherical. If all those conditions are okay, and you illuminate a number of them and you have a single light scattering, then you could divide the two and get the two signals and get something related to the southern mean diameter. Of course, you need to calibrate the system, and this is not a constant, it's a calibration curve, and this you can do it with PDA. So we did it. So here is a holocone water spray containing some fluorescein with a PDA. We illuminate at 447 to excite the dye, and we get fluorescence in the green, yellow region. So now we've got the three images where we move the line structures for the leaf, now the same for the me. If we just make the average of those, we got the conventional images. So here, once again, we can see we have some information above the light sheets that we should not obtain. We have also signal in the middle of the spray which should not be there, or not as strong. And if you divide the two, you have this ratio here, and we try to calibrate this. The problem was that for a given ratio, we obtain two values, two PDI values. And that was because the big droplets outside of the sprays, they were giving similar signal to the small droplets inside. So it was obviously wrong. You couldn't calibrate the system. And the spray was not even very dense. So you should really be careful when you do conventional imaging for this Leave Me sizing. Now we did exactly the same with the SLIPI. Here it looks, we remove the light intensity above. It looks white, but actually there is a signal here. It's just the color bar doesn't show it. Now if we take the ratio of it, we have this image showing large droplets on the outside of the spray and small toward the hollow region. Then we calibrated it, and in this case we got a single solution for each ratio, which was a very good sign that calibration was possible. So finally, we obtained a 2D droplet size. But you can see that in this region here, it shows small size. So this is not, it's not supposed to be this way. So as I said, the technique works only for spherical droplets. And in this region is a spray formation region. You have ligaments, you have liquid structures that are not spherical, and you have to ignore this region. The technique doesn't work there. It works only when you have a cloud of spherical droplets. So you have to also be careful on this. Always measure when you are sure it's matching the condition of the technique. All right, so what about now thermometry? Instead of dividing a me signal with a leaf, we can divide two leaf signals with a different spectral band. And this dye is actually temperature sensitive. So if we heat the liquid from 20 to 80 degrees, there is a shift of the spectrum toward the red. If you put a filter, you have this part increase while the first part is decreasing. So by taking a ratio of those two bands, you can actually figure out the temperature. So what we did is first we tried it in a small cuvette, in a cuvette just with water and dye. It's working fine. Still, we can see the thermocouple behind the light sheet, and we can see some signal outside of the light sheet. And curiously, when you take the ratio, this is also changing, but it doesn't show the same than the signal in the light sheet. So you have some effect of reabsorption and remission of the dye that are responsible for this. But when you do SLIPI, at least you clean up this. You don't see as much the thermocouple anymore, but the big difference is the sensitivity. So here we go from 1 to 3 in a ratio, from 25 to 85 degrees, while here we're going from 1 to 9. So of course the conventional is still working, but the SLIPI approach is giving a better sensitivity. Those are the response of the two color ratio as a function of the temperature, with the difference between SLIPI and conventional, and we can see the response of SLIPI being higher. And this means that the sensitivity is better, and it's actually increasing with temperature, which is something we need to understand a little bit more why. If you look at the relative sensitivity, it shows that the SLIPI technique is between 2.5 to 6 times higher sensitive. So then we applied it to the same spray, and we increased the temperature of the liquid, and we could observe the change in 2D in the spray. So all of those results, they were based on average imaging, because we need these 3 images, and it means it's very difficult to record very quickly, so we did all of this on average imaging. But of course, what's interesting is instantaneous imaging, is to freeze the motion and observe the dynamics of the spray. So in this section, I will talk how can we possibly do this technique single shot, which was also one of the first questions. So this is the optical arrangement. So technically, how do we do? So this is optical arrangement from the measurement I showed you previously. So we had these CW lasers. We just expand the beam, take the central part of it, flat beam, and we have the sinusoidal grating, one cylindrical lens that creates an image of the grating into the spray, and another one that creates a light sheet at the place you create your image. So it's not very complicated. The grating needs to be fixed on a traverse that is accurate enough that you can move at the right phase. So this is for average imaging. Now, how do we do for single shot? First, you need a pulse laser. Then you need to do this 3 times. So you need to use 3 lasers, 3 gratings. You recombine everything, and you need to change the camera, because you need to detect those 3 pulses in a very short time delay, in this case 125 nanoseconds, because you want to freeze the motion of the spray. You don't want from one image to another that the spray has moved, so you need to do it really fast. So then you need 3 ICCD cameras or a multi-frame camera using the 3 ICCD chip. So using this setup, we have recorded the first instantaneous SLIPI back in 2009. And you can see the improvement between the two. So the hollow region appears hollow, same thing than before. The droplets are enhanced. You see better on the SLIPI image. Voids are visible. Some voids you couldn't see on the conventional, now you observe them. So this is very interesting, but still, it's a quite demanding setup. What you need for this setup, you need 3 ICCDs, 3 laser pulses. You lose 90% of the energy because of this recombination. It's a complicated arrangement. It's not everybody who would like to do this arrangement with all those grating, and it's expensive. If you do with 2, you can use a double frame SMOS camera, which is 10 times cheaper. You can also use only 2 pulse laser, and the arrangement is much easier. So we can still question, why not doing with 2? So as I said before, it's not possible mathematically. But still, from an optical point of view, it's very advantageous. So let's double think about it. What about if we try to make this residual line as small as possible, and then try to remove them? To remove lines on an image, you need to do some low-pass filtering. So here is a test target, and here's the zoom of the area. So you can take the FFT of this image, and then we can fix to 1 the maximum allowed frequency visible on this image. And now we just cut it in the Fourier domain. We inverse Fourier transform it. And then we can observe that between the results with filtering or without, the main image, the big structures, you don't see much of a difference. But if we zoom in, we can see that some high frequencies have obviously disappeared. So we are removing lines. That's what we do there. Of course, we do a trick and we modify a bit the image. So what about trying that with a technique? So here it's modulated subimage. We start with very low frequencies, so very big lines. Now we take 2 of them, we subtract them and take the absolute value of it, and then we get this image. And what you do is actually we create this residual at twice the frequency of this one. So the lines here are twice as small. Now, what's happening if we increase the frequency of the first modulated image? So what's happening is we are pushing away the frequency components. And if we go to quite high frequencies, now those if we subtract the 2 images, we start to push it far away from what is visible. So the trick is to go to high frequency, and then we Fourier filter it, and we filter it just below the frequency of the residual lines, right? So now we've got this, we inverse Fourier transform it, and we have this image. How do you know it's good? We need to compare with the 3-phase SLIPI. So this was on average, because we need to make sure we do correctly. And this was the 3-phase SLIPI and the 2-phase, and they look really similar. So if you do it with low frequency, the filtered and the 3-phase, they don't look the same at all with a lot of artifacts. You increase the frequency of the sub-images, now it's reducing, and now the 2 looks really similar. And your eye cannot even, at some point, see the trick. So we then did it on a single shot, or let's say instantaneous imaging in the spray. And if you zoom in this region, you don't observe any residual lines. So the benefits you've got is very big. Now you can observe some small droplets here that you will not really see otherwise. Okay, so we have proved we can do it. We should now apply the technique for real-world application. So in this section, that's what we have tried to do. This is how we were doing with the 3-phase SLIPI. Now we can do it with 2, as I just showed you. So we get back to our cheap camera. But still, you need 2 sinusoidal grating, and you need to arrange them. So there is a little bit of optical arrangement. What about if we recombine this way? Then this is like a standard PIV system, recombined with a polarization beam splitter, so you don't lose any energy. And you have a grating here, and what you want is now to move very fast these structures. And mechanically, you cannot really do it. We are talking about hundreds of nanoseconds. But you can do optically by using a calcite crystal. And the advantage of these crystals is you have different refractive index as a function of polarization. So the vertical polarization will be slightly shifted vertically, while the horizontal polarization will go straight. So you can design these calcite crystals with the right thickness to make the exact shift you want, as a function of the frequency of your grating. So by doing this way, you're not limited in time. You can do as fast as you want, and the optical setups becomes very simple in a way. So we applied this optical arrangement to a GDI spray. If we zoom in, you can see the modulation. In this case, it was an ethanol spray at 2,000 microseconds after the start of the injection. All right, so now we sum up the two images and we take the average of it. We take the average, and this is a conventional. So the lines are disappeared, and this is what you will obtain with a conventional laser sheet image. And now if you do SLIPI, you remove all the background light. And these background lights are from the other plume. This was a 5-hole injector. So you have 4 behind, create these background lights that appear when you illuminate, obviously. And then you clean it up, and you see the individual droplets that you could possibly track, while before it's hidden in the multiple light scattering. The voids inside the spray are really enhanced. So now this is really what you got in your light sheet, not around it. So what's interesting is to look at the differences, the variation from injection to injection. And this is quite interesting in this case. You can see how turbulent is a system, and a lot of post-processing could be done to analyze those sprays. Now if we look at 250 microseconds later, so the spray has moved further down, we can see that there is a reduction of light intensity. In this case, it was liquid laser-induced fluorescence. It was not mis-scattering, just... and then, again, 250 microseconds later, so at 2,500 microseconds after injection start. Now you can also compare different types of fuel. This was ethanol. What about butanol? And this is the case for butanol. Both cases were injected at 160 bars pressure. And the spray here, you can observe that it penetrates further in, and there is a bit less voids in the structures. So depending on the fuel, even though you inject at the same condition, you can clearly see variations, and you can analyze them better with the SLIPI technique. And then at 2,500 microseconds. Okay, so now you can also take a ratio of, you can do that with a leaf and the me, the same than before, and extract. In this case, it's not calibrated, so you cannot say this is the exact droplet size, but you can have an idea of it, and you can do single shot imaging of it. At least you can remove the effect of light extinction and signal attenuation. So those images of ratioing are still interesting, but they need to be post-processed a bit further and be calibrated to put an exact number on the droplet size. All the upper part here, you should not consider it, because once again, you have these irregular liquid structures. You should use high-resolution imaging and try to really image the feature over there to resolve them. So I guess the question is now, what about two-phase SLIPI, particle tracking velocimetry? And we actually got just the results last week, so I cannot show it, unfortunately. We didn't post-process. But what I want to say is, from a hardware point of view, it's not complicated. This is what we have for a single image. And of course, if you add another PIV laser, recombine it, and you need the expensive camera again, then you can do it. But from an it's just a hardware demanding. It's not, I mean, it's just camera and lasers. But from the optical arrangement, it's the same. So this is the next step, and we will present it in the future. I think it has been a lot of small conclusions in the talk, so I don't want to say all of them again. I hope you have been convinced of the capability of the technique for sizing, thermometry, and looking at dynamics. Very importantly, I would like to thank Elias Christensen, who has been co-inventing the technique with me and has been working the last 8 years together on this. I would like to thank Yogeshwar Mishra, with my PhD students who worked on the averaged LIFME droplet sizing and thermometry. And as well, he also, in the GDI sprays, Yogeshwar worked with Matthias Kolg in LTT, together with Lars Zigan and Michel Storr. So those measurements in the GDI sprays, they were done at the LTT Erlangen. I would like also to thank the financial support from the European Research Council, the Swedish Research Council, LaVision, and the School of Advanced Optical Technology. And finally, I would like to thank you for your attention.
Thank you very much. We have about 7 minutes for questions. Cam, is there a microphone?
Okay. Thanks. Wonderful explanation. Nevertheless, I would like to ask maybe a critical question, maybe not so easy to ask. So you have these, let's say, use the three-phase lines,
Yes.
and you have your camera here, and so there should still be multiple scattered photons collinear with those lines that make it into your camera.
Yes.
Yeah, and my question, and I know you've done a lot of Monte Carlo calculations. This is not something you can measure, but you can estimate then whether or not there's a residual error due to those collinear photons, or whether, and that's my question, whether it's canceled out with the three additions and squares. It's not clear to me yet whether you get rid of that. And I don't, and the real question is, if it's still there, does it give you any error, residual error, let's say also in the thermometry? Do you understand?
Yes,
right?
I do understand. I think it's a very good question. Actually, yes, when you look at the phase function, so of these droplets, you have this highly forward lobe, and a lot of the lights for 10 microns droplets will have a tendency to keep forward. I think if photons are not deflected from their direction, then you can use this light to illuminate the next droplets. But as soon as you get deflected, it will cancel. The thing is now, if you want to be quantitative and you try to simulate the problem, you try to calculate the extinction coefficient out of this measurement, you will underestimate the extinction coefficient because of this forward scattering. So you will think you have less particle in your medium than if you had very small droplets. That scatters more. It's not isotropic, but more round, light spread around. Now I don't think if you take a ratio, I think it will cancel, because the energy that goes straight and excite droplets and you have miscattered will also induce a fluorescence in a similar way. So both of them should benefits of this. But this effect of the size of the particle is very interesting because it blurs the image differently. You have different blurring if you have small particles or big particles. And that's something with a simulation you can understand and you can try to. But for time gating, it's not in your advantage to have big particles, because then there is a small deflection and photons doesn't spread in time.
My question is why the 3 image is enough, or can you go further to 4 image, 5 image?
Yeah, I mean we can go for more, but usually you don't want to go for more. But it's true. We did up to 12 on average imaging, and try to look at if the final image is improved or not. And we didn't find any improvements. So if you do 3, 4 or more, you don't really improve the suppression. But what is very important is the frequency. If you have very big lines, then the suppression is not as efficient as if you go to smaller line structures. So it's more important to change the thickness of of the lines structure, or increase the frequency of the modulation, rather than having more and more and trying to do the process with 3 or 4 or 5. But of course, if you want to go for a single shot, you don't want to do more. Sure. So you can also do with 1 if you want, but then it will be lots of information you will miss. For a spray, I don't really recommend it because you have those tiny droplets. If you do this processing with only 1, you will miss a lot. But if you have a flame or a flow with a smooth curve, you could do the process with only 1 image and post-process. But you lose image resolution, but you gain in optical setup.
Another question?
Thank you.
Yes, I would like to come back on your two-band imaging of temperature in your spray. And if I have well understood, you observe a kind of difference between the sensitivity using regular illumination and SLIPI illumination.
Yes.
Could you come back on that? I don't really understand this difference. Yeah, okay, you suppressed the bottom signal, okay,
yes.
you using, but it's in a cuvette here.
Yes. This is no scattering. That's why this is where it should really work. It's not even. We started just to try to see what is the effect in a cuvette. So there is not even much scattering. But this is a fluorescein dye, and the absorption spectrum is overlapping with the emission. So you have a self-absorption and re-emission, and that's why you got all the signal around it. But one could think, anyway, this behaves the same when you hit. So when you take a ratio, okay, you can have a signal outside of it, but it should follow. It should be the same ratio, which is not. And this, we need to think more. Why?
Okay, this is a kind of secondary fluorescence. Is that?
Sorry?
It's a kind of secondary fluorescence.
Yes.
So this is reabsorption and re-emission.
Yes. Yes. Exactly.
Yes,
it's not scattering.
Yeah,
no.
That's not scattering.
No.
It's secondary fluorescence.
Correct.
Okay.
Yes, correct.
Thank you.
Okay, one last quick question.
Yes, in fact, I think that I have the answer if you come back to the slide before. But in fact, it is that the absorption of fluorescein is temperature dependent.
Yes.
And it is much more dependent on the temperature in the band you have chosen for the filter one, where there is this recovery between emission and absorption.
Yes.
But for the secondary absorption,
Yes.
it also happens at lower wavelengths, where it is much less dependent on the temperature. So that's why secondary absorption, secondary emission of fluorescence, in average, is less sensitive to the temperature than normally. Yes.
Thank you.
Okay, thank you very much. That was a really beautiful presentation, and I'd like to close the session where we have a couple of minutes before we start the regular sequence. Thank you.